She did a lot of work under her PhD at Arizona State, my alma mater, so you go Sun Devils. And graduated in 2014, and then since she's been involved in all kinds of field research programs where she goes into the field at an analog site. It might be an analog to Mars or the moon, and does work like an astronaut might do in that particular situation. Collects data that tries to give them information about the site. So she's been involved, I guess, in the Desert Rats program. There was an impact crater, I'm blanking on the name of it.
Cotton.
And she's also worked on Black Hawk lava flow?
Black
Point lava flow in Arizona. And then also work in the Lava Beds National Monument in California. She's done lots of field work on Hawaii and probably some other places that I'm forgetting. She'll tell us more about them today. But a lot of this work is focused on trying to understand how to do field geology on other planets. So today she's going to be talking to us about how to integrate field portable instruments into that kind of exploration. So please give Kelsey a warm welcome.
Thanks everyone, and thanks Nick for sort of helping me set up and coordinate this visit, and thanks to all of you who I've already spoken with today. I'm really psyched to be here. I spend a lot of my time in the DC area, and I used to work at Goddard, and I still telework sometimes from Goddard, so I'm really passionate about working in this area, and I'm excited to be here at the Geology Department today. So like Nick mentioned, so I'm going to sort of talk to you about sort of the history of crewed planetary surface exploration and sort of where we as NASA see it going in the future. I sort of today wanted to give you a really broad brush overview of all different types of projects that I'm working on associated with NASA-funded research to look at how humans will explore planetary surfaces in the future. So rather than delve into one project, I wanted to give you a flavor for a lot of the projects I'm working on to sort of give you a sense of what NASA's interested in doing and potentially how some of you could get involved in the future if you're interested. And one of the things specifically that I've worked on a lot on is field portable instruments. So in Apollo, the astronauts were basically working with sample collection and storage technologies to bring samples back to Earth to study in labs. But in the future, we're going to have higher resolution in situ analytical capabilities for surface exploration. So I'm going to talk to you a little bit about sort of the overall operational field test by which we test full mission simulations, and then spend the bulk of the time on field portable instruments in general, and then the astronauts who are going to be using these things for real in the field. So obviously, we've spent a lot of time in the science community studying the solar system. We've sent missions throughout, even past Pluto, past the end of our solar system. But we've really only sent human beings right to the moon. We've never sent it past the Earth-Moon system. So what do we want to do in future to get us ready to build out from that and potentially, hopefully, one day take us to Mars? So obviously, we've been to the moon. We sent 6 people to the moon from 1969 to 1972. But as I mentioned, they were mostly focused on sample collection. They had about 3 EVAs per mission. EVAs are extravehicular activities, so spacewalks where they traveled over the lunar surface. And they were mostly just focusing on mapping the area, collecting samples, storing them, and returning them to Earth, where scientists are still today studying samples, and I'm sure including some of the people in this room. They did deploy some surface science experiments, specifically, for example, heat flow measurements and seismic experiments, but they really didn't have high-resolution analytical capabilities because in the 60s, those technologies just didn't exist at the size where astronauts would actually be able to deploy them on the lunar surface. They did have the lunar roving vehicle, so this little car that they were actually able to use on Apollo 15, 16, and 17, which enabled them to get farther away from landing sites than ever before. And if you looked at the science return from Apollo 15, 16, and 17 versus 11, 12, and 14, they were able to travel a lot farther and collect more diverse samples than ever before because of the addition of this new technology, the lunar roving vehicle. So keeping that in mind, we want to discover new technologies like that, which without too much overhead will be able to enhance the science return of future crewed surface missions. So why do we do this? We were talking a little bit at the grad student lunch about sort of scientific motivation for why we send human beings to other planetary surfaces. So there are sort of 3 target destinations or classes of bodies that NASA is interested in sending humans to. So of course we have return to the lunar surface. Hopefully at some point soon, astronauts are once again going to put boots on the ground on the moon. We also one day want to build outward toward the journey to Mars and toward putting people on the surface of Mars. And then we also have small bodies. So how many people here are familiar with the ARM mission concept, Asteroid Redirect Mission? Yeah. So up until a few months ago, NASA had ARM on the books to retrieve a boulder from an asteroid, bring it into lunar orbit, and send astronauts to the boulder to explore properties of small bodies. And while that's no longer on the books, NASA is still looking at mission concepts that include Phobos and Deimos, which are the moons of Mars. They're small bodies in orbit around the red planet. So that's still sort of on the books as a potential target for human exploration. So it's important to understand how these small bodies form and evolve. So while massive advancements have been made since Apollo, there are still obviously a number of outstanding science questions across all three classes, Moon, Mars, and small bodies, that human exploration could really help answer. Obviously, there are concerns here. Planetary protection, we also talked about that at lunch a little bit. Planetary protection are big concerns, especially when we're thinking about Mars exploration, but there are a lot of compelling science questions that we can answer by going by sending people to these three types of exploration destinations.
Does NASA exclude exploitation?
So NASA right now is looking at in situ resource utilization. So they are interested in sort of harnessing resources that might be on other planetary bodies to help with human exploration. But at exploitation, I like to think it's more exploration than exploitation. But maybe a difference of... I think NASA is mostly focused on answering compelling science questions, not looking at exploitation of other planetary bodies. So when we're thinking about exploring small bodies, the Moon and Mars, there are a lot of things that we have to consider when we're looking at architectures for human spaceflight missions. These include variable communications delays. So it can take as much as about 15 minutes one way for a communication signal to reach Mars, and then another 15 minutes round trip. So looking at how you interact with a human crew at or around Mars is really complex when you considering how to have human operations under long latencies like that. Obviously, these different types of bodies have different atmospheric and gravity conditions, so understanding how humans can operate under these different conditions is really important, and it's something we as a community need to understand what this will be like prior to actually sending human beings here. So a lot of what I'll talk about today is focused specifically on operating under these variable conditions. And again, another thing we talked about at lunch, flexible technology development is crucial. So NASA does not have a plan right now to send humans to a specific destination. We're working on different mission concepts, and I'm hopeful we'll have one pretty soon here. But right now, we as a science community really need to focus on developing technology and operational concepts that are flexible for all of these environments. So when one of these mission concepts is actually decided upon and funding starts to flow, we as a science community are ready to respond to that. And so basically what I do at NASA is, half of what I do is answering science questions about planetary surface processes. So I spend my time looking at volcanic processes and impact cratering processes that shape this planet, but also the surface of the Moon and Mars. But the other half of the time, I spend working with the human exploration community. So actually working with the engineers and operators who are actually going to be flying these missions when we send human beings into space. And also working with the astronaut community, because these are the men and women that are going to be holding these instruments in their hands one day. And so what I want to advocate for, especially with you guys as a big part of representing a big part of the science community, is that early integration with the human spaceflight community is really crucial to accomplishing our science objectives as a community. So I would encourage all of you, if you're interested in lunar and Martian science, to really early on start thinking about how you might adapt your science to mesh with the human exploration community, because it's not something that's going to happen overnight or immediately. It's something we need to start thinking about now. And there's history of this, right? Not just Apollo. It's not, scientists and engineers didn't just work together on human spaceflight in Apollo. Just an example that I wanted to highlight is the Lunar Reconnaissance Orbiter. So the Lunar Reconnaissance Orbiter was at the time jointly funded by what's called the Science Mission Directorate at headquarters, which funds scientific research, and what at the time was called ESMD, but what's now called the Human Exploration and Operations Mission Directorate. So this was a mission that was flown for two purposes. One was to answer compelling science questions about the Moon and its history over time, and one was to actually explore landing sites for future human missions. So this is a perfect example of two directorates at headquarters working together to fund a mission that would benefit both communities. And this is exactly the type of thing we need to model in future if we hope to successfully put boots on the ground again. And so their instrument payload was selected specifically for both of those purposes. So all of these instruments were competitively selected and chosen because they could answer science community's questions about the moon, as well as help select landing sites for future lunar exploration. So this is just one example of how traverse planning from LRO data is basically being facilitated by the types of instrument payloads that we have on LRO. I really like these pictures. The LRO was actually able to image all of the Apollo landing sites, and you can actually see boot prints of where the Apollo astronauts actually explored the moon. You can see their traverse paths and where they drove the lunar rover. They can actually see what's left of the lander there on the lunar surface. Another sort of success story of LRO was one of the boosters from the Apollo 16 mission. They ejected them on purpose, of course, and it hit the lunar surface, and we've never been able to figure out exactly where it hit. But because of the high resolution imaging capabilities of the Lunar Reconnaissance Orbiter, they were able to find the booster impact site and observe exactly where that hit on the lunar surface. So, but we want to move forward, right? And we have been, of course, completing missions since Apollo, even though we haven't been back to the moon. We have the International Space Station. We have astronauts up there right now, and they're observing Earth. They're making active observations about the active surface processes that are shaping our planet. They're conducting science experiments in microgravity, figuring out how materials and the human body function in this microgravity environment. And they're doing this because it takes a long time to get to Mars, right? The astronauts that eventually go are going to spend about 6 months one way getting to Mars, and we need to understand how their bodies are going to be changing before they get there so that when they land, they're actually able to complete their science objectives and their EVA objectives. And we need to understand exactly how the human body is going to be responding in that microgravity environment for such long periods of time. But what about surface operations? So technology has come a long way since Apollo, and we don't really understand how these advancements in technologies are going to look when we eventually complete surface exploration again. So that's what my research focuses on, and that's what the rest of my talk will focus on as well. This is an eye chart, so don't try to read it. But what I'm trying to show you here is NASA has a whole suite of activities that are preparing us for human surface exploration in the future. We have the Apollo missions, of course, which even though they're over, we're still incorporating lessons learned in our operational architecture planning for future exploration. We have the Mars rover missions. So of course there are 2 active rovers on Mars right now, and the rover teams that drive them, the scientists and engineers who are responsible for rover mission operations, are doing this under these long Mars latencies. So we're understanding how to do surface science right now with these Mars rover teams, and we're learning a lot from them. We have the NASA Nemo mission, which is a series of missions. We just completed the 22nd one that has crew members living underwater off the coast of Florida in a habitat that teach us how to do operations in extreme environments. I'll talk about that a little bit more. We have the Desert Rats missions, which are a series of Habitat Rover tests in the Arizona desert that I'll talk about a little bit more as well. And these are bigger operational field tests that put scientists, engineers, technology developers, astronauts all together in one simulated mission environment, which is the best way. This end-to-end testing is the best way to really stress the system and evaluate where we still have gaps that we need to fill for surface exploration. But we also have these smaller funded analog projects that put smaller teams of scientists out in the field working on things like instrument development. So I want to talk about Nemo, Desert Rats, and some of the smaller campaigns that I'm working on right now to give you a sort of sense of the breadth of the activities that NASA's looking at right now to sort of build the science concepts and operational concepts for the future. So the way I'm sort of looking at this is you sort of start from an integrated testing perspective. So I want to talk to you about those bigger mission simulations, and then focus in on the actual instruments that I'm thinking that astronauts will be using on surfaces in the future. And then, of course, those instruments are nothing if they're in the hands of untrained crew members, right? So I'm going to talk to you a little bit about how we train crews to understand the lunar science and Martian science and science of our planet, so they can observe that from the space station right now. And all of these things will lead to successful exploration missions. So field testing in relevant environments is obviously not a new concept. All the Apollo astronauts had hundreds of hours of geology training. So with basically the amount of training they got, essentially each astronaut that flew had the equivalent of a master's degree in geology by the time that they launched on their mission to the moon. And they were doing this in relevant environments. So for example, this is the Apollo 17 crew, Jack Schmitt. Who knows Jack Schmitt? only geologist to ever go to the moon, and his crewmate Gene Cernan, testing out technologies that they were going to be using on the moon in Arizona, and that you can actually see the cameras that they used mounted to their chests during the Apollo missions. They tested the rovers, of course, in relevant environments, and they went out with field geology trainers to learn about the specific landing sites that each crew would be visiting. So field testing of technology and understanding surface processes in analog environments has always been a crucial part of preparing for exploration, and we're continuing that work today. So we test in multiple different types of environments right now, and I'll talk to you in depth more about several of these, but I wanted to give you, again, a bigger picture view of the type of environments that astronauts and scientists and engineers are training in right now to prepare us for the future. We have aquatic facilities, so we have the Neutral Buoyancy Lab at the Johnson Space Center, where they have mock-ups of the International Space Station that they can train for EVAs on. They have the Aquarius Reef Base Facility, which is where they run the Nemo missions, which I'll talk about. European Space Agency, which is one of our major partners, has their own pool where they train astronauts in. We also have terrestrial environments, where I think a lot of us are more familiar with. We have these sites where we do these bigger full-up field exercises, like desert rats. We have specific sites where we actually take astronaut candidates, so astronauts who have not yet completed their initial training programs, where we take them to train them in field geology. We have extreme environments like Antarctica, where scientists and astronauts go to understand how to do science in these extreme environments. And we also have laboratory analyses. So we have things like Argos, which this is a guy hanging in a harness. It's called the Active Response Gravity Offload System, and it can simulate microgravity, lunar surface gravity, Mars surface gravity, to let crew members and scientists and engineers understand what it feels like to work in these different gravity environments. We have virtual reality and hybrid reality labs, so we can put crew members, scientists, and everyone involved in human spaceflight physically on, in another planet while you're sitting here in the lab. And I'll talk to you a little bit about a hybrid reality project that I'm involved with. And then International Space Station is a laboratory, right? It's a testing ground where we can prove some of the technologies that we need to send us further out beyond low Earth orbit. So the first sort of thing I want to talk to you about is these bigger full-up mission simulations, these integrated operational field tests. So these combine science, ops, and technology in this mission-like environment. And the reason we do this is because we can test out these concepts of operations on a natural surface, similar to what we're going to be doing for real, as a team, as a big integrated team, because all of these folks will be needing to work together to do this on the moon, and we need to practice it now on Earth. It allows us to test hardware and tools for not just science tasks, but pioneering tasks like building habitats or building landing sites, or basically just doing things that enable crew members to survive. And then we test these tools and techniques that will enable the communication between Earth, between the mission support teams, and with the astronauts actually doing the EVAs and doing the surface exploration. And we can do this over an appropriate communication delay relevant for lunar and Martian exploration. And we do this using what's called a flexible execution methodology, flexecution. And basically what that means is that the astronauts go in with a plan. They go in with a traverse. They go in with a plan saying, I'm going to go from here to here to here to here. But they're doing reactive traverse execution, right? So if I see something that's not directly on the path that's written on my map for where I need to go, I'm going to be empowered to actually make that decision to change the traverse path based on what I'm seeing real time. So we want to empower the astronauts and the technology that they're going to be using to accommodate this flexecution methodology. And I'll talk a little bit more about it moving forward. So NASA has a lot of analog projects that they're involved in. All of these little dots represents a different analog project that NASA has going on right now. And again, we're doing this because these future missions are really going to be long in duration, and especially if we go to Mars, they're going to be far from home. So we really need to understand how these analog surface operations are going to work, and that starts with early end-to-end testing of these OpsCons, these operational concepts, and these hardware in this flight-like environment. And the thing that's important to realize is that a lot of these analogs don't just benefit exploration that's going to be taking place potentially decades from now. They benefit ISS as well. And ISS, International Space Station, again, we have crew members up there right now, and it's really important that we continue to enhance the type of science that they're able to do on ISS. So the first integrated test I wanted to mention is desert rats. It's called Desert Research and Technology Studies. And so this represents an integrated team of engineers, of scientists, of astronauts from all over, NASA centers, from academia, from DOD, from DOE, from military. We even had high school participants. They had participants actually from multiple different countries that worked together on these desert rats field tests that ran for over a decade out in the deserts of Arizona. This is north of Flagstaff in the San Francisco volcanic field. You can see some cinder cones in the background. And the goal of this was to test this hardware, software, operational concepts to identify and establish what the requirements are necessary for eventually moving forward to doing this on other planetary surfaces. So this is what I call the Desert Rats family photo from the 2010 test. So you actually had these Habitat Rovers that 2 crew members at a time could live in. They're docked to a Habitat Lab. So there were actual instruments in there that could analyze rock samples that the crews collected real time. They could they had a lab where they could do things like repair a spacesuit if there was damage to the suit. And they had basically different modules inside that lab where they could do different things pertaining to long stays on other planetary surfaces. They had this little guy who could, move small amounts of earth and gear around, and they had this big guy called Athlete where they could move really heavy cargo around. So if you're going to be staying on a surface for a long period of time, you want to be able to, to shift gear around, and Athlete could help them do that. So just to give you sort of a flavor of the types of stuff we were looking at, we of course were testing the Habitat Rovers. So here's a view of the cockpit. The 2 crew members would sit here and they could drive the rover and look at camera views from outside on these screens. So each crew had 1 astronaut and 1 field geologist in the crew, and that was the astronauts. Many of them had already flown, and they could tell the engineers something about how to design things like the cockpit to make it a little bit more high fidelity for surface exploration. And the geologists were there to say, hey, it'd be really helpful to maximize science return if you had this additional piece of hardware, or you change this to make it a little bit more straightforward from a software perspective from looking at data. So the operational concept that we were developing is this 2 rover scenario where you had 4 crew members on a surface at least, and you had 2 crew members in each rover that were driving around the surface of the moon in this case, and collecting samples and bringing them back to the lab. So we evaluated the Habitat rover itself as well as operating 2 rovers simultaneously. We were also evaluating sample collection technologies. So we started with the Apollo-style tool design and iterated from there based on feedback from the crew members. And this sort of multi-year test environment allowed you to design it, then test it, then redesign it based on feedback, then test it again. So this iterative process really enables pretty quick turnaround on incorporating some of the lessons learned from the field testing. And then you had the Habitat Lab, like I mentioned. So here's the lab. In 2011, we actually added a little habitat on top that was inflatable that actually had things like bunk beds in it for the crews to sleep in. This is the Geologic Glovebox. So you could actually examine samples that you had collected on EVA inside the glove box and actually start to analyze them in situ and get a feel for what the geochemistry of these samples were like. And here's sort of a zoomed out version of the glove box. Here's where your hands go, and you could look at the data displayed real time on these screens. And you could also send this data back to your mission support team on Earth, or in this case, back in a hotel room in Arizona, to have your mission control team help you interpret the data you were getting real time. So from an operations perspective, we were testing how to do integrated EVA science operations. So as I mentioned, you had these crew members out on EVA, and they were supported by a huge and wonderful mission control team back on Earth, or back in a trailer, or back in their hotel room. So we were looking at this operational concept that had this ability to interact between the EVA crew and the mission control crew over varying comm latencies. So for example, we had a 15-minute one-way communication time. We had a several-second one-way communication time to test the difference between how this communication structure and the volcanic eruptive history of this area. So we're still getting really exciting science out of projects that work in these analog environments. So the next sort of integrated mission I want to talk to you about is Nemo, the NASA Extreme Environments Mission Operations Test. It's an acronym within an acronym, next level for NASA. So the crews live and work from this Aquarius Reef Base facility in the Florida Keys. So this is the underwater habitat. It's located 6 miles offshore from the Florida Keys, and it's in 60 feet of water. So crews live in here for a couple weeks at a time, and they simulate working and living in an extreme environment. We're working on ISS objectives for International Space Station, as well as objectives for exploration EVA on unknown surfaces like the Moon and Mars. And just like Desert Rats, we have participants from all across the agency, from international partnerships, from academia, from industry, and combining that, we're able to produce some really exciting science. We have international crews. This is the Nemo 21 crew from last year. We had participants from the US to Europe to South Africa, and it was really exciting. We were able to do a lot of in situ coral science here, and actually we were even able to do some mini DNA sequencing, which you might have known made the news the last year or so. We've actually been able to sequence DNA in space, and right before the first astronaut did that on station last year, we tested it in Nemo 21 underwater. So the science we're doing with Nemo is not quite as relevant to Mars exploration because we're not doing geology, but it's still really exciting and compelling science, and I'd be remiss if I didn't mention it. So we're basically doing coral reef research, as well as looking at coral nursery construction. So one thing we're doing is building these coral nursery trees, and we partner with the Coral Restoration Foundation. So you can actually see this looks like a pretty big tree. It's about the size of a person and has all these arms on it with what looks like little credit cards hanging down from the arms. And each one of those cards is one card with a specific type of coral growing on it. And we're looking at what species of coral grow best at which depths to start repopulating some of the coral reefs that have been damaged. And just something I think is super cool is that last year on Nemo 21, we built the deepest coral nursery ever in the world. So we built a coral nursery at 90 feet, which is the deepest one anywhere. So it's really exciting nursery science that we're doing with the Coral Restoration Foundation and learning about how we can start to repopulate some of these damaged reefs. And then we're also exploring and doing active marine science with, partnered with the Florida International University Marine Science Lab, and we're looking at why these reefs are dying, what diseases are being passed between species, and why, to start to understand exactly how to fix this problem worldwide. And the benefit of doing this with Nemo is that these crew members who are living and working at Nemo are doing it while saturation diving, which means that when you scuba dive, you can only spend an hour or so at the bottom of the ocean, but when you're saturation diving, you can get a lot longer hands-on time with some of these species. So we're able to do some really exciting and important, I think, scientific research through Nemo. But we're also testing operations. So this is a complex diagram, I know, but basically what this is showing is you have a science team who's sitting on a trailer on shore on the Florida Keys, and that's populated by scientists from NASA like myself who work on how to do these operational concepts for real, as well as marine scientists whose research is based around this coral reef research. And then you have the science team talking directly to people inside the habitat. So these are 2 crew members who are sitting at a console inside of the habitat, basically looking at all the data that's coming in, looking at all the communications that are coming in from us on shore, as well as from their buddies who are actually out doing the EVAs. And so that's what's reflected here. You sort of have this console position as an interface between the science team and the astronaut who's out on EVA. So we're looking at all the different types of communications that can go between these 3 different players, whether it's texting, whether it's voice, whether it's video, and what's going to be needed when we actually do this on Mars so we can start to develop the technology that's going to facilitate this in the future. So sort of some of the takeaways that from Nemo the last couple years is that we've been able to exercise communication of all different types between all 3 of these entities and really converging on a model that we think makes sense. And just to give you an idea of sort of one of the results that we're finding is that basically when you're operating under a time delay, it's 30 minutes round trip for you to send a communication and get one back. So if I say, hey, how was your day? You're going to get that 15 minutes later. And then you think about it. You say, it was okay. I kind of had a problem with this. And that's going to get back to me 15 minutes later. And then I'm going to say, okay, well, you could fix it by doing that. And you see what I'm saying. It takes forever to actually send any meaningful communication back and forth. And just imagine doing this when you have a crew member out there on Mars who's in a potentially dangerous environment, and you're trying to make sure that that person is safe and healthy while still trying to get valuable science, and you're doing all of that under a time delay. It starts to be a lot, right? It starts to be a lot of information that's going through a really small pipe, and you need to understand exactly what type of communication you want to be sending and getting back. So what we're finding is that actually what the astronauts like when they're working under these time delays is only texting between the science team and the person who's sitting inside the habitat. They don't want to hear our voice, right? Because they're going to get a voice communication that I sent from Earth 15 minutes later when they're kind of in the middle of something and they're busy and it's going to interrupt what they're doing. So they want something written that shows up on the screen in front of them that they can divert their attention to when they have a second, when they're not dealing with something critical, and they can react to what we're saying at a time, at a pace that's appropriate for them. And then they, because they're not under time delay with their buddy who's right outside, can voice that concern or that question or that comment to them when there's an appropriate time to do so. So it's this type of communication loop that we're fiddling with now, and that it's really important to test ahead of time so we can start to build the technology now. So what are these technologies? I just wanted to give you a couple examples of the type of technology development that we're doing with Nemo. One thing that we're doing is looking at informatics. So what would you want as an astronaut on the surface of Mars that's helping you to collect samples and store them for return to Earth? So what we're actually working with is what's called this cue card system, where it's a touch button system. You can actually touch that and get a procedure to run through, or you can get sample identifying information that helps you figure out what coral species you're looking at. So we deploy these informatics on an underwater iPad, believe it or not. Apple's everywhere. And so you're actually clicking through all these buttons. We have over 150 different options of procedures and sample identifying information that you can look at on these informatics. And the crew members are doing things like identifying samples with them, learning how to run through procedures. This is just an example of a procedure that they can pull up real time. And that permits, when you're operating under this time delay, it increases crew autonomy. It empowers them to be able to do things without having to wait for a reply from Earth, which is just wasting valuable time, valuable surface time. So through developing these informatics and figuring out exactly what type of information we as scientists want the crew to be able to have, we need to test them in these environments. We also want to work with things like what the crew wants, not just on EVA, but inside the habitat helping their buddy, right? So this is like a very overwhelming picture, but it's pretty realistic, because here's the person who's during an EVA, he's sitting inside the habitat helping to coordinate the EVA activities. And these are all of the streams of information that he needs to be monitoring at one time. It's a lot of information, right? He's monitoring whether or not they have enough oxygen, how much time they have left remaining on the EVA. These are actually communications from the science team that are coming back to them. They have video feeds that are, like, believe it or not, off to the side right here that are the helmet cams of this person's buddies while they're out on EVA. So, and they also have things like, this is the speaker by which he has to talk to the science team. This is the speaker by which he has to talk to the crew. This is a timer to keep track of instrument analysis. So they have just 1,000,001 things that they're having to monitor at one time. So we're looking at things like, where does each screen go? Where do you want the screen that shows video? Where do you want the screen that shows the actual mission log that you're communicating to mission control on? Where's the screen where you want to understand how healthy the crew is doing, where you're monitoring their vitals? This person is responsible for doing all of that, and it's really important to test exactly what kind of information they need and where it needs to go ahead of time. So now that I've sort of framed the bigger picture for you and you understand all the variables that are at play here, we want to look at actually what the astronauts are going to be doing on EVA and what type of instruments they want to be deploying. So when I say instrument, I think everyone in this room would probably define instrument a little bit differently. And even just the number of conversations I've had today with you all have been really interesting, just to see sort of exactly what types of science you guys do and how it differs from one another, and exactly what you mean by analysis or instrument. So what I mean is basically any sort of higher resolution in situ analytical capability that an astronaut would have to increase the science return of a mission. And what you want to do is maximize that science return while not giving a really big time hit to the crew member that has to be operating it. So I don't want an astronaut to be operating an instrument that takes 3 hours to run, right? Because that's 3 hours that they could be spending doing something else. And if you're only on a surface for, a few hours, a few weeks, a few days, you really want to be able to maximize how much you can fit into that time, and clicking buttons on an instrument for 3 hours is probably not optimizing that time. So you trade off, how much science and exciting, compelling science return you're getting from that instrument versus the overhead of having to incorporate that into what you're doing as a crew member. And I think the benefits of instruments influence sample high grading. So if I have 10 samples, but I can only take 5 of them back with me, which 5 do I pick and what instrument's going to help me decide which 5 I take back? But it can also inform you real time to say, wow, this looks like one lava flow, but this instrument's telling me there's actually potentially 3 different eruptive events here. That's probably going to impact what I do for the rest of that EVA. So these instruments can have a lot of important impact on astronaut timing and EVA planning, and it's important to develop an instrument suite that tells you a lot of things about the surface that you're operating in. So the project that I work a lot with is called RISE, and it's funded through this virtual institute that's jointly funded between the Science Mission Directorate that I mentioned earlier at headquarters and the Human Exploration Operations Mission Directorate that I mentioned earlier. And so these are all projects that are funded that have benefit both in exploring science of the moon, small bodies, and Mars, as well as that science having an impact on human space exploration. So for example, the team that I work on studies field portable instruments for astronauts, and it also studies the toxicity of lunar dust, right? So it's really any type of science that could have an impact on human space exploration. And the team that I work on is called RISE, the Remote In Situ and Synchrotron Studies for Science and Exploration team. And the piece of RISE that I really work on is this field portable instrument question. So basically our methodology for RISE is the following. You start with a science question. What do you want to know about the lunar surface, for example? And you, in order to answer that science question, come up with a suite of technologies, a suite of instruments that can help you answer that question. So then you go out in the field to answer that science question with the suite of instruments that you've chosen for in situ analysis, and you basically test the validity of that instrument suite in answering your question. And then the unique part of this project is that then we provide recommendations toward the human spaceflight community for how to design these instruments, both hardware and software, for when they actually fly in space. So the field operational architecture that we use for RISE is basically, and first of all, this is a kite image, which I think is really cool. It's taken from a camera mounted on a kite that's actually looking down at what we're doing in the field. And really, we decided to use the kite because UAVs are banned in Hawaii, which is where we were working. And so, but UAVs are okay as long as they're tethered. So as long as you have a camera that's attached to you, you can circumvent that issue. So this picture was actually taken from a kite. So we have this crew down here, which is again an astronaut and a geologist, to again be able to test these operational concepts from multiple perspectives. And then you had these instrument teams, which are each operating a different field portable instrument. And so in this way, the crew is actually able to complete their EVA around the site of interest. They're actually able to, pick up rocks, collect them, store them for return to Earth, to simulated Earth. And then they're actually able to say, man, it'd be really nice if I had this type of measurement here and this other type of measurement over here. And the instrument teams would come along behind them and take those measurements. So by that, we can actually evaluate how valuable that scientific data is versus how long it takes the instrument team to collect that specific measurement. And just for RISE, we had a series of science journalism students out with us too. So we partnered with the Science Journalism School at Stony Brook University. And these are students who are learning about how to write about science. So they're coming out with us to learn how we do science in the field. And they're learning from us just like we're learning from them. So our field site, our original field site for this project is on the Big Island of Hawaii. So we're in the southwest rift zone of Kilauea volcano. So do we have people who've been to Hawaii Volcanoes National Park? Lots of people, yay. So if you've been there, you've been to probably the overlook, the observatory, the visitor center. And that's right here on the edge of the active Kilauea caldera. So if you've been, you've probably been right where this pointer is. So the flow that we're looking at actually comes right down from that caldera, all the way down almost to the ocean, which is down here. So this flow erupted from a series of fissures right here and flowed down and around this cliff face that bounds, that makes up the edge of a fault. So we've been working here for a number of years, and we're studying the flow emplacement, the chemistry of the flow, how it alters along the length of this really long flow, and how the flow has altered over time. So the reason that we selected this field site is because it looks a lot like what we see on the moon and Mars. So it's a desert environment, but it rains occasionally. And so what you see here is you're looking upflow toward that caldera, and you can see this active plume coming up from the caldera here, and then it's coming back down over where you're working on the flow. So you have this sulfuric gas plume that's coming out of the caldera, and when it rains, it pushes that plume down on top of the flow, and it creates these really interesting coatings. You can sort of see it's like kind of orangey in here and a little white in places. Some of the coatings in the field actually show up as this like really bright iridescent blue color, and that's formed from these sulfuric gases interacting with this basalt. And interestingly, a lot of these alteration products in chemistry and mineralogy look like a lot of what the data from the Mars rover is sending back. So these alteration products have direct relevance to some of the alteration products we're seeing on the Mars surface. So we're trying to study how these might form and how rover relevant instrumentation can pick up more about how these things formed. So what instruments do we bring out in the field with us? We have instruments that sort of work from a broad field of view. So if I took an instrument analysis right here, I could get all of you in the frame in different wavelengths. So we have multi and hyperspectral imaging. We have a LiDAR, a tripod mounted LiDAR, which gives high resolution surface roughness and surface texture. We have ground penetrating radar. We have the kite that I mentioned. And for in situ chemistry and mineralogy, we have handheld X-ray fluorescence and portable X-ray diffraction that we take out with us. And most of these instruments have direct relevance to an instrument that is either currently on a Mars rover or will be on a Mars rover. And we also think that a lot of these technologies can be made portable for an astronaut to hold in their hand if they're not already been miniaturized to that extent. So the types of science that we're investigating at the 74 flow with these instruments is really variable. So like I said, we're evaluating the alteration coatings, and we're combining handheld X-ray fluorescence, X-ray diffraction, and multispectral imaging to look at what these coatings are made out of. We're looking at areas of hydrothermal alteration, and these areas are called the solfatara at this site. So that's where there's latent heat from previous volcanic eruptions that's coming up through the flow and creating these areas of hydrothermal alteration. And the reason scientists are really interested in studying these on Mars is for two reasons. One is they tell you something about heat that's left over, and it could represent some sort of active surface process on the surface of Mars. We also have, these areas are really compelling astrobiology targets because we think that that's where some sort of microbes could still be left over if there's any life to be found on Mars or any signs of past life on Mars. However, some of these products can be pretty toxic for human health. So while they're areas of really high scientific interest, they're also potentially dangerous for human explorers. So it's really important for us to understand how these things form and how an astronaut could use a handheld instrument to tell him or her if the area where they're walking into is potentially dangerous to their health, or whether or not it's okay to proceed to collect these really compelling scientific samples. And we also do things like, I just love this picture, I think it's really interesting. So we're looking at things like flow morphology and emplacement. So what we see here is, you can see this little dot of lighter material surrounded by this darker material. And what's happening here is that darker material is that younger flow that's been emplaced on top of the previously existing topography. And so you get what amounts to islands sort of in the middle of the flow. That's an 8.5 by 11 sheet of paper, that white dot right there, for some scale. And what's interesting about these is that it looks, and maybe this isn't the best example, but there are some islands at this flow that looked like sort of channel bar deposits like you see in fluvial systems. Obviously, this is not a fluvial system, right? This is clearly volcanic. So when you're looking at remotely sensed data of Mars, you have people arguing that features like this can only be formed in a fluvial environment. And what we're learning is that is just not the case, right? You can get these islands, these bars, these channel bar looking deposits in volcanic environments too, which tells you something about the water budget and the water flow on the surface of Mars. So it's important to understand morphology and emplacement from the ground so we understand what we're seeing from the air. But operationally, what's the hit of getting all of this really interesting science data out of field portable instruments? How does that affect your timeline as a crew member when you're deploying these things in the field? So while this increased science value is really important and it tells us something about the geologic history of an area, what hit does it cost you to your EVA timeline, and how do you have to buffer in time to use these instruments on an EVA? So what we do is actually build off this same Desert Rats mission construct that I talked to you about earlier to develop these operational timelines. So I want to give you just one example just from one instrument as a simple case to show you what I'm talking about. So just one example with the handheld X-ray fluorescence spectrometer, which gives you in situ chemistry in just 60 seconds. you actually have, this is the Desert Rat Study Area, so this is the geologic map of the area. So when we were completing these EVAs in 2010, we could clearly tell that this younger flow was a lot younger and a lot more different than the flows around it. So that was erupted really recently. The flows around it really looked pretty similar from remotely sensed data. So when we planned the traverse, we didn't really know how many flows there were, of how many different generations of eruptive activity there were. And you know, when we were in the field doing this work, it was even hard to tell when you were looking at the hand samples. So with the exception of this really young flow, all the other basalt in the area looked basically identical. It was really hard to tell one sample from the next, and I was one of the crew members, and I was having a really hard time distinguishing between hand samples because these EVAs that we're on are about half an hour long. You have no time. You're getting out, you just want to collect the sample and get back in, and it's really hard to say to yourself, you know, I collected a sample 3 days ago that kind of looks like this, but I can't really remember because you're so rushed to make sure you can really get a lot of science done and make sure that you're getting back to the rover on time. So it's really challenging to tell the difference between different types of lava flows here in this area. But when I went back and I analyzed these same samples with this handheld instrument, we were able to clearly identify 3 different lava flows from those samples that we collected. So when you're collecting the data with these handheld instruments, you're able to really identify one flow from the next when you're not necessarily able to do that just with your eyes and with your observational skills in the field. So when you plotted those back on the traverse map through the area, you're able to actually pick out where these flows come from and where they originate. So we were actually able to pick out one flow that went off to the west of this SP crater flow, as well as one flow that went off to the east toward the Black Point lava flow. And so just in this just tiny little case study with one instrument on 10 samples, you're actually able to tell something that you're not able to real time in the field. But what does that cost you? And it costs you about 2 minutes per sample. So every time you take one of those measurements with these field portable instruments, that's an operational hit you're not going to be able to spend somewhere else. So you really need to understand the operational implications of using one of these instruments because while you may get interesting data back, it might not necessarily be worth it when you look at the operational cost of using it. So what we've been doing now with RISE, now that we've sort of started to identify what instruments might make sense in these analog environments, is look at things like the informatics the crew needs to interpret the data. So while you may be deploying 5 instruments at one time and being able to use them over days at a time, that's a lot of data. That quickly becomes just an overload of information that you're getting back. So I might have 100 XRF measurements that I've taken and 100 different point analyses of chemistry, and that's great, you've collected so much data, but can you act on it? Is it actionable data if you don't understand it because you're assimilating so many streams of information, you're not able to really understand exactly all the stuff that's coming in. So what kind of informatics do you need to develop to help the crew member process all of this data in time to act on it? Right? So what we're doing is looking at informatics and how we might design some sort of informatic, like I mentioned in the Nemo mission, to really assimilate this data, process it, and create figures that help you interpret what's going on from a high level, because that's really all of the time that you have time for. So we did, similar to the cue cards I mentioned during Nemo, we did something like that for RISE. So here's our field site. From just one EVA, we have 5 different types of data that we're starting to process and display in this way. So you can see this sort of brain dump data flow that you can start to assimilate multiple different types of data stream into something that the astronaut could pull up and say, okay, 3 days ago, I saw something that looked a lot like this. Let me go back and just double check what I'm seeing is accurate. And so by that way, you can start to pull in lots of data, but actually start to interpret it and piece it together in a story, rather than just having an instrument in your hand and being able to see days worth of data as you scroll down the screen and not really be able to put it in the larger context of the site that you're exploring. So we're taking it one step further with a project that was just funded. So we just had this project called Scientific Hybrid Reality Environments funded. So this is the same field site that I just showed you, that same lava flow in Hawaii. The ocean's like way down here and the vent is way down here. So this is part of the December 1974 lava flow that we work on. And just a couple of things to note about this. You see these big sort of plate-like features here. That's actually because as the flow was erupting, it came up against a topographic high right here, and it actually, got dammed and got stopped. And the top of the flow, since it wasn't moving, started to solidify and harden. But underneath, the flow was still moving because that part of the flow hadn't hardened yet. And eventually, it breached this dam that had formed right here and flowed off toward the ocean. But in the meantime, that hardened crust had started to crack up from the strain of that magma that was still moving underneath it and started to raft apart these big plates. So you see that these big plates had actually been broken apart from one another, knocked against each other, and started to flow downhill when the dam broke and the flow continued downslope. So you actually had, once those plates rifted apart, you had a space where younger magma was actually coming up in between these plates. So you can actually see multiple generations of eruption from the same larger flow event right contained in this one field area. And you also have things like one of these streamlined islands that are right here from above that could really look like something fluvial, but is clearly volcanic in nature. So just in this one sort of flow section, you have a lot of really interesting volcanic processes taking place that a crew member, if they were to come across this flow on Mars, they'd want to investigate further. So we picked this field site for that reason. There's a lot of compelling science questions that we want to investigate. And we also picked it because we have years worth of portable instrument data. So we've been operating on this flow for a number of years with a really big team of scientists from across NASA and academia. And so we have all of this, photographic data and instrument data that we're now going to incorporate into what's called hybrid reality. So if we take all this instrument data together and recreate this flow in something that you can see with some sort of virtual reality glasses, you can start to create this flow in the lab so that when we want to do things like test instrument concepts and how we would deploy this instrument versus this instrument, you can actually do it real time in the lab without having to go out in the field. So what we're hoping to do with this project is actually recreate a Mars or Moon relevant environment in the lab with virtual reality. You can see this person's wearing the virtual reality glasses. And it's called hybrid reality because what you see in the screen, you can actually start to interact with in the real world. So if I am viewing this computer desk in virtual reality, I see the mouse, and I can actually, in actual reality, pick up and interact with the mouse in and of itself. So you can actually start to really interact with your environment and learn what it would be like to actually pick up an instrument in real life and actually deploy it in the lava flow, put it up to a rock in the virtual reality scene, and get real data coming back, because that's data that we had collected previously on this lava flow. So we're trying to progress all of these instruments and create a high fidelity testing environment, both in the field and in the lab, to train crew members and understand exactly how these processes evolve over time. Yeah?
Do that with the Apollo sites, or just not enough resolution of the data from Apollo?
Yeah, so the reason we picked this site in particular, so I would argue the same could be said for the Mars rover landing sites, right? So why didn't we pick to create the Curiosity landing site or the Apollo landing site, right? And it's because, let's just take Curiosity as an example. You have really exciting rover data from Curiosity, but you only have it where that path went, right? You only have the data where the rover drove. And if I wanted to go over here in hybrid reality, I wouldn't be able to because there's nothing there, right? So we don't want to recreate something that followed a specific traverse path. We want to create something where I could go over this entire room and be able to explore the entire room if I wanted to. So you want to create some element for the crew members to make their own decisions about where they want to go and not necessarily follow the predetermined traverse path. That's a really good question, and it's one I wrestled with when I was writing that proposal. So another project that I just wanted to mention briefly, and how are we doing on time? Okay, is the TubeX project looking at lava tubes. So lava tubes are a really interesting exploration concept because we think that could provide a radiation safe haven for crew members. So we're actually looking at how to deploy field portable instruments in a lava tube environment to pick a tube to select to harbor humans and gear from this potential radiation environment. So tubes are really interesting because they could be this radiation safe environment, but they're really complex in terms of geometry and size and in shape. So we went to this tube-rich environment and deployed field portable instruments to tell us how to explore them. So we had differential GPS, we had a LiDAR that I mentioned earlier, we had a ground penetrating radar, we had a magnetometer, and Ernie Bell was out with us. Here he is, right above the lava tube here. We were deploying seismic arrays, and we were deploying handheld geochemical analyses and using all these instruments together to develop a lava tube exploration strategy. which basically goes that you can take these LiDAR scans from inside the tube, actually figure out what these tubes are made out of, and both of these two technologies together can help you interpret the data that you're getting from the ground penetrating radar from above. And by using LiDAR and in situ chemistry, we're actually able to determine if GPR and if magnetometry are reasonable techniques to use to explore these environments. So field portable instruments can be highly beneficial, but there is a cost to using them, so we need to continue to investigate how we might use them. And just really quickly, because I know I'm out of time, but just we want to follow on with the successful science training model that was used in Apollo by using it with the current astronauts right now at NASA. So some of the things that we're doing with crew training are we get them before they actually graduate to become full-fledged astronauts. We get them during their astronaut candidate years, and we train them the basics of the geology, both in the classroom and in the field. And then we do things like we take them out and train them in these analog environments and on these smaller deployments. So this is astronaut Don Pettit out with Nick and Ernie and I last fall in the San Francisco volcanic field. And we teach them how to deploy these instruments that I just was talking about. We teach them why geology is important, why surface science is important, and why they need to learn it before they fly. And then we put them in situations where they can test that knowledge. This is Kjell Lindgren, who just flew on station, and he's applying that geology knowledge in a full-up mission simulation environment. And so and when we teach them things like that, we get images like this. So this is one of the great success stories of geology training of astronauts. So we got them excited about volcanology and helped them understand why it's important on shaping our planet and other planetary surfaces. And this was a picture taken by a crew member from International Space Station. And what happened was he was flying over this area and saw a volcano erupting that he didn't think should be erupting. He hadn't heard that there was an eruption in this area. He didn't think that was quite right. So when ISS came around again, he had his camera out and he took this picture. And he was actually the one that alerted us to the fact that there was even a volcano erupting in this area. And it's because he understood enough about volcanology and why it was important to recognize it and take this picture. So I'm just going to leave it here, and I can take questions.
So the lava tubes was one of the last topics you covered, so it's freshest in my mind. But you said that they're havens of radiation, which they are, from galactic and solar top and radiation, which makes them also viable places where biosignatures may be preserved. So do you consider that in your training modules, A, how to maybe sample those locations as potentially scientific points of interest, but also how to minimize contamination control?
Yeah, so that's a really interesting question. So it's kind of frustrating that if we're evaluating life on Mars, all the places where we think life on Mars is going to be, we can't go because of planetary protection, right? So you get into this like feedback loop of never actually being able to go or sample anywhere because you could contaminate it. So it's a really big problem, and it's not just lava tubes. It's really any type of environment we think where there might be signs of life. It's the same issue that you're talking about. So what we're trying to do right now is evaluate the types of technologies that could detect it so that once we get this planetary protection thing worked out, we know if it's going to be an astronaut holding that tool in their hand, if it's going to be a rover or some sort of other autonomous vehicle that goes in so you don't have as much contamination concern going in. But what we're trying to do is understand exactly what types of instruments would detect those bugs and signs of life and how to operate them. And the other thing about lava tubes in particular that isn't true for sort of the other astrobiology sites of interest is that human safety comes first, right? So if you're on a planetary surface and there's a radiation event coming and there's really no other place for that crew member to go, that comes first, right? So human safety comes before science objectives, right? You want to get your crew members home safely. So in the case of lava tubes specifically, if that's really the only place for astronauts to be safe on the Martian surface, that's what comes first.
I'm curious about the selection of the analog sites because the two sites you showed are both volcanic fields, but every time we land a rover or a lander on Mars, we go to the sedimentary basins. So are there other analog sites we use?
Yeah, so I just picked a couple. There are so many different analogs that are just like, they're great for different reasons. And it's not just scientific analogs, it's operational analogs as well. So there can be analogs for all different types of spaceflight, but you're right, it's certainly important to explore environments relative to, more relative to sedimentary basins on Mars. You're absolutely right. A lot of sedimentary deposits on Mars actually originated in basaltic environments because there's just so much volcanism on Mars. So a lot of sedimentary units we see actually originated in basaltic terrains, and that's why 74 in particular is really interesting in Hawaii, because a lot of the eroded materials around it, these sedimentary units, are eroded volcanic units themselves. So there's a lot to consider when you select the analog site, and it just depends on the exact question you're trying to target with that field campaign. But your point is extremely well taken, that you really need to explore a wide variety of scientific analogs when you're thinking about surface exploration. It's a really good question.
So a lot of your operational design is based on this intravehicular and extravehicular team,
Yeah.
but then you have limitations about how fast they have to work, how long they have to go. And I'm just wondering why you even have an extravehicular team. I'm thinking of all of these lessons we have from the deep sea floor exploration, where you have either submersibles where you are protected and you can stay there for some time, or you have remotely operating vehicles. Why even want to have people connecting these things and not using remotely operating robotic devices?
Yeah, it's a really, really good question. And so, for example, the Mars rovers have been really successful on Mars, right? They've answered lots of really exciting science questions, they've raised new science questions, and they've been really successful in collecting a lot of scientific data. Just to put things in perspective, the Opportunity rover has been operating on Mars for over a decade, and it just hit the 26-mile mark, right? So it's gone about 26 miles, just over 26 miles in over a decade, right? So we just don't have the robotic technology yet to be able to even come close to rivaling the amount that a human being could do on a surface. So the technology isn't there yet that's space hardened enough to collect even close to the amount of scientific data that we got from the Apollo missions, for example, and that was in the 60s. So we don't have the technology at a high enough level that's been able to fly in space yet to start getting to where we even are with oceanographic science, because even the science that you're talking about for oceaneering is even farther along than some of the technology we've flown in space. So maybe one day we'll get there, and maybe, for example, one day the robotic manipulators will be good enough that they can work with fine-scale features that are some of the most compelling features, exploration targets on Mars. But right now, we don't have the type of technology that's at a high enough TRL level to fly to start to really get to maximize the science return from some of these missions. But it's a really important question that I think the human spaceflight community needs to be really aware of pretty much all the time.
In terms of the instruments that you guys will actually take, there is probably some constraint limitations. So how do you prioritize which instruments go? Is it just cost, or is it? You mentioned science returns, but is that goal related, or is that just data?
Yeah, no, that's again also a really good question. Probably first and foremost is cost. I mean, that's always going to be a big concern from a NASA funding perspective. And another point to consider is mission architecture. So if you're going to be staying there for a couple days at a time, you're going to pick way different instruments than if you're staying for a long duration mission. So it really is I think, it falls on the shoulders of the scientific community to get the technology to a point where when we do decide on a mission, we have the technology that's able to fly it. So I think that it's a frustrating answer to your question, but I think the answer is it depends. It totally depends on the type of mission. How many crew members are going to be on the surface? How long are they going to be staying? Are they going to have in situ lab time on the surface? Are they going to, if it's in the case of Mars, are they going to be able to use those instruments on the 6-month transit back to analyze the samples they collected? It totally depends on the architecture and the target body that NASA selects, which I know is not a super exciting answer. Flexibility is key.
Bill,
Yeah, commercial flights. Is the NASA interfacing with people who are anxious to do that?
Yeah, so NASA's
And when might we see something?
So NASA's really excited right now about commercial partnerships, partnering with several different commercial companies, some of which are already flying cargo to the International Space Station. So we've already seen some of the results of those commercial partnerships actually fly in space, and it's no small task to be able to get rated to fly to International Space Station. So they've already come a long, long way already. But companies like SpaceX have come out and said that they want to go to the surface of Mars and the Moon. Power to them. I think anybody who can get science instruments or people to other planetary surfaces is really exciting. And NASA's really committed to these commercial partnerships because it's a mutually beneficial relationship. So one of the models they're considering are leveraging these commercial companies to the point where the commercial companies are responsible for low Earth orbit, which frees NASA up to go farther away from Earth. So that's one motivation for these early commercial partnerships. But I think that's one of the directions the agency is moving, for sure.
Yeah, I have one more. Mine's about money. So you're talking about instrument development. Are the instruments that you guys are testing in the field, are those primarily funded through ROSES, as in Picasso, Matisse, P-Star? Because I would imagine that there's a HEO is there not a HEO program that invests in miniaturizing it for field applications rather, because it seems like Picasso and Matisse are autonomous operations. They're kind of like, they seem geared towards landers
Yeah.
and stuff.
So Picasso, Matisse, and P-Star programs that he's mentioning, for those of you who aren't aware, are programs that are funded through the Science Mission Directorate to get instrumentation ready for spaceflight. So it's to enhance the technology readiness level of specific instrumentation so that it's ready to the point where it could be selected by these big mission proposals. You touch on a big issue, right? And I think the bigger picture issue from what you're saying is that Science Mission Directorate and the HEO Mission Directorate, Human Exploration Operations Directorate, are two separate directorates, right? They don't overlap, really. There's some overlap, but it's minimal. So the answer is no. HEO is not really funding instrument development for science right now. It all falls on the shoulder of the science community. And that's because we don't have a surface exploration program funded right now, right? So most of the money that HEO puts out goes toward International Space Station objectives because they're just not funding a surface exploration program right now. I think I'm hopeful that if a program gets funded, which I think could happen pretty soon, depending on how things shake out, we might see a shift in that. For example, one of the groups I work with a lot at Johnson Space Center is the Eda Tools Group. So these are the engineers who are responsible for physically designing the hardware that the astronauts will hold in their hand while they're on EVA on International Space Station. They're not even, I'm working with them a little bit. We're just at the beginning of this working relationship. They're just starting to think about this because we think that surface exploration hopefully is going to be upon us again soon. So I'm hopeful that at some point the tides will start to shift, but right now it's SMB that's funding it.
Can I have one last quick
One last question, and then we'll take it up for
No,
geology.
because I'm glad that Bill mentioned the commercial companies are trying to fly and do the space flight. But that's go back to the beginning, as Bill says, the exploitation versus exploration thing. Does NASA think about how do you, I believe that in NASA maybe our goal is to explore, to expand our knowledge, but for commercial companies, how do you think about policies and some ideas before things happen and get into troubles? What's the general thought about that?
Yeah, so things like asteroid mining.
Yes.
And things like that. Yeah, so there are companies, again, for those who aren't aware, there are companies out there who exist for the sole purpose of things like asteroid mining. We talked about this a little bit at lunch, but commercial companies who are just getting into this, we're just at the beginning of this sort of new mode of space exploration, and NASA definitely has offices at headquarters who are concerned with dealing with things like planetary protection, of which this is a valid concern. But we're right at the beginning of working out issues like this, so it's going to become an issue if these companies look like they're ready to fly. I certainly don't work in the planetary protection office at headquarters, so I won't speak for them. But it is going to become an issue for sure, and it's something that NASA's going to have to reconcile.